Family of graphs. All right. First thing I guess I really want to start off with is we're going to do some Desmos. Because I'm going to talk about what different graphs look like. Y equals x squared. Does everybody know what a graph of an x squared looks like? Parabola. Parabola this way. All right. If we were to make this x cubed, what would happen to this? It makes the line go this way. The same thing happens on x to the fourth. It's a bigger parabola. All right. Notice how it comes out this way. And x to the fifth is the same thing. Notice how it flattens here a little bit more before it goes down. These are families of graphs. So any kind of even exponent set up in here is going to give you a parabola look. Anything that's odd is going to give you this type of look. This is called symmetric about the origin. All right. Whereas anything with an even number is symmetric about the y-axis. All right. If you get into different terms like square roots, where's my function on my square roots? Am I missing it? Oh, right here. Square root of x. Square root of x can never be negative, can it? If it is, it's an imaginary number. So if you take a look at how our parabola goes, or one half of it, it goes off to the side. All right? That's a square root. If you were going to do it as an absolute value, what does the absolute value look like? It's a V. Absolute values always are V's. Okay? That's an absolute value. These are families of graphs. So if you understand, if you see something with an even, bless you, if you see something with an even exponent, you know pretty much what that should look like. It should look like this parabola. It looks like a cup. If you see something with an odd exponent, then it kind of looks like a backwards S, or almost like an S, shaped. All right? Square roots only come off one side, and the absolute values are always a V. Always. These are called families of graphs. Going into another one, if I was to put 1 divided by, that looks pretty silly. Really? I had to do that? Y equals 1 divided by x. I want you to take a look what happens with this one here. We never can equal 0 with this, right? Because if we had a 0 here, then this would be an undefined number. But it gets close, and it goes back up. All right? This is another one. We don't work with this one too often. You won't. I guess in my experience, you're not going to see this too often. The ones you're really going to be working with a lot, especially as you go into calculus, is going to be the parabolas. You're going to work a ton with parabolas. Okay, so x squareds, x to the fourth, those type of things. As you get into calculus, being able to revolve, let me put up an x squared here once. and I'll show you a little thing that's going to happen when you start working with parabolas, is you're going to start revolving this shape around this y-axis. And you're going to determine on a limit, let's say from 0 up to 6, what is the volume of this revolving shape around this axis. And you'll be able to determine what the volume of that is. As you get into calculus farther, you're going to work with things called integrals. Okay? And integrals are, let me just give you a little example. It looks like this. And I'm going to say from 0 to 6 of x squared dx. That's an integral. Okay? And this is how you would use it to be able to determine what my volume is from here around here if this shape is spinning around that axis. It gets pretty cool because now you can start determining, you can determine what the shape of or what the volume of something is. And one of the examples that I used this for actually in a job that I was working for a foundry machine shop, and they also did fab work. And they had two pipes that came in like this, and they were soldering these or welding these pipes together, right? And the weld on this actually came like this. And a pipe came down and then it came up and here. And here's where they filled this weld, right in here. And what this estimator asked me, an engineer estimator asked me, he said, and this is, you can imagine this weld's going all the way around this, right? He asked me, he said, can you come up with a program so we can estimate how much weld we're using on each one of these pipes depending on the diameter and also the type of weld. This is just one example of a weld they use. I want to know how much weld I'm using on this so we can figure this into the price and we can come up with a better solution, you know, when we estimate better out when we do this fab work. I said, yeah, I can do that. I took this type of thing here and I figured out what my volume was going all the way around this, using this. With what he determined, what they used for what scraps, so there's a little bit, you know, not all of it's used. And, you know, let's say not all the stick is used or something like that. So he gave me the numbers, and I did up a program for him, and he took it, and he started using it, and he says, you have no idea how close you are. He goes, we are so close. He says, we're going to use this as part of being able to charge customers where we couldn't do it before. So it was really cool to be able to use something like this. So a lot of what you're going to see going forward, especially in calculus, is going to be something on the parabola type thing because you're going to make shapes. Could you use something like x cubed? Sure. You could, but your shapes are going to look completely different here. Put 3 in there. Now you're going to let's say you would go from -2 to 2. What would your shape look like? Kind of like an hourglass, wouldn't it? So you could determine the volume inside that. So if you were to take an hourglass, all right, and depending, you figured out, and you took it and you were able to map out saying, okay, this is more like, let's say, a x cubed, and my hourglass is going to come like this. When I revolve this shape around here, here's my hourglass. And I want to be able to determine how much volume is sitting in that. All right, you'll be able to do that. One of the really neat and fun things to do in calculus. All right. So, what's that? You're in Pre-Calc, but that is, yeah, pretty much. All right. But learning these family of graphs is really the first part of what you have to do. Now, there are 3 terms that I'm going to want you guys to what do you mean? You won't, yeah. These two, or this graph and, yeah, this graph right here, I don't even worry about. You won't see that. I'm not worried about that one. That is not in the calculus world. You should never see it. All right, reflections. If you take a look on page 121, a reflection would be, I should have kept Desmos up because this has been neat to look on Desmos. No, wrong one. I'm going to run two different graphs here. I'm going to run x squared, and then I'm going to run another one here of a negative x squared. See what happens to my graphs. One is a reflection of the other, okay? And all I did was add a negative to it. One made a reflection of the other one, all right? Reflections, usually it's going to be off a negative value that's going to switch it around. In fact, if you take a look at it, they have y equals a negative f of x and y equals f of negative x. Creates reflections. If you look at the y, well here, this one here is based off of the x-axis right here. And this one is based off the y-axis. Okay. Now, what's that? Okay. So you get an idea of what reflections are. Let's take a look at translations. If I was to take x squared, could have left it up there, I suppose, x squared, and now I took and I added a value to it, x squared plus 5. You'll see what happens. Oop, wrong way. You'll see what happens in my graph. It literally moves my graph up 5 spaces. This is called a translation. If I was to put it as, let's put it in parentheses and add 5, x plus 5 parentheses and then squared. Notice what it does now. My translation would not be moving it up, but would be moving it, instead of a plus 5, a negative 5 on the axis. Do you remember when we worked, did we work with absolute values last year? Do you remember when we worked with absolute values, how if we had it outside of the absolute value, it moved it up and down on a graph? Do you remember that? And then if we put it inside the absolute value, it was always the opposite of what this was. X squared works the same way. All right? It works the same way. If I was to take another one here and I was to say x squared minus 5, it'll move it down. All right? I moved it down. And if I take another one here and I say parentheses x squared, no, I don't want to do x squared there. Minus 5 parentheses squared. Notice it moved it over here. All right, these are called translations. I'm able to take that x squared graph and I'm able to move it around on my graph coordinate. Okay? That's called a translation. Take a look on page 122, they called delineations. Reflections are pretty easy. Translations should be pretty easy. You should be able to see that. A delineation now is when I take, let's take x squared, and I look at that graph, and now I go out to another one, and I'm going to make this x to the fourth. And what happens between these two is called a delineation. Why did it go down there? Oh, I did a square again. You silly thing. Yeah, I can do it here. There. Notice what my graph does. It starts going wider and it comes up narrower inside. These are dilations. Okay? If you take a look at some of the examples, they're putting a constant. They're multiplying this by 2 out here. What happens to my graphs? Let's get rid of this one. All right? I should probably, let's do this. I want to do it as separate ones. Let's multiply this one by 4x squared. And what happens to my graphs? It's changing that graph nature. It's actually keeping the vertex of that graph where it changes directions at the same point, but it's changing the nature of this graph. It's making it wider. It's making it skinnier. It's doing something. These are called dilations. Okay, dilations in graphs. All right? Those are the 3 that you really need to do, to look at. Guys, here's what I want you to do on this, on 21, 22, and 23. Yeah, I want you to do 21, 22, 23, and then I want you to do, I guess, 21 through 27. Is really what I want you to do. I want you, can you take it? Here's what I want. Do you have to graph them? I would make sure you know how, if you had to graph it yourself, how to graph it without Desmos. All right? Make sure you can do that using the XY table. If you know how to do this and get it, that's what I'm interested in. What's 0? Oh, in this case, 0. What's 1? Then it's 4. And I'm looking at 4x squared here. What's 2? It's 16. Okay, what's negative 1? It's 4. All right. What's negative 2? It's 16. So I can start graphing. If you know how to do that, all right, then all I'm really interested in you doing is looking at Desmos and trying to take a look at what these look like. That's what I want you guys to figure out. What does this look like? I want you to do them. I want you to write the graphs down. I want you to have them on paper. As long as you know how to do this and you can determine that graph, I'm good with it. All right? If you're not sure how to do this and you want to do some of this, then use numbers like this to determine what it is. See if you can figure it out. See if you come up with the same coordinates you would see on Desmos. All right? So what I want you to do is 21 through 27, page 123. Okay?